Hello, everyone. My name is Ravit. I'm a professor at the University of Zurich, and I'm going to tell you about the formation and evolution of giant planets. First of all, why is it important to understand the formation and evolution of giant planets? Giant planets are not habitable like terrestrial planets, but they're very important planets to investigate, and this is because of two main reasons. First of all, they shape the architectures of planetary systems. This is because they're very massive and they form very early, and therefore they can excite small objects and lead to delivery of volatile materials. For example, in our solar system, we think that Jupiter was responsible for bringing a large fraction of the water we have on Earth. And the second reason is their composition provides information on the physical and chemical properties of protoplanetary disks where all planets form. And this is why it is very important to understand and characterize giant planets. Maybe the most important take-home message of my talk is shown in this slide, which basically tries to connect planet formation, planet evolution, and planetary internal structure. The point is that the formation process determines the primordial internal structure of giant planets. And this primordial internal structure, so the way the composition is distributed after the formation process and the thermal state of the planet, determine the long-term evolution of the planet, which will, in return, will determine the final structure of the planet, or the current state structure. And the point is that these three aspects of planet formation, evolution, and internal structure are linked, and therefore we have to study them together and understand the interplay between these different aspects. So first, a little bit about giant planet formation. Currently, there are two main models for giant planet formation. The first one is known as core accretion. This is the standard model. And the idea is that in this model, giant planets, they begin to form like terrestrial planets by planetesimal coagulation and core formation, followed by accretion of a gaseous envelope. The core formation can also be a result of pebble accretion, as I'm going to show you a bit later. But the idea is that the beginning of the formation of a giant planet starts with the solids and the buildup of a core. And only once a core which is massive enough is formed, then gas can be accreted from the disk, leading to the formation of a gaseous planet. But this is kind of a critical point. So without the formation of the core, the idea is that you don't going to form a giant planet. Then we have an alternative model, which is known as the disk instability or the gravitational instability model. And in this model, the idea is that giant planets could form as a result of local gravitational instability in the protoplanetary disk. You can see it here. The idea is that at early times, the disk can be massive enough, and then a local gravitational instability can occur, and this region can collapse and lead to the formation of a gravitationally bound giant planet. Long time ago, we thought that if these are the formation processes, it would mean that in the core accretion model, there should be a relatively massive heavy element core, while in the disk instability, this is not the case, and that the core accretion model typically leads to giant planets that are highly enriched in heavy elements, unlike the disk instability model. But now we know that actually each formation model can lead to a very large range of compositions and internal structure. So actually determining the planetary composition and structure is insufficient to constrain the formation mechanism. But in the solar system and around many other stars, when we observe giant planets, the core accretion model can explain most of the properties. Nevertheless, the disk instability model does seem to be required to explain some of the processes some of the systems that we observe. So the disk instability, as I said, the idea is that giant planets form as a result of disk fragmentation. You can see it in this simulation. Again, you have the development of spiral arms when the disk is massive enough and cold enough, and then you have the formation of these clumps that can evolve to become gas giant planets. This fragmentation typically occurs at large radial distances. It can be associated with the 2-mark criteria, which you see here, Q, and you can see the parameters here. And basically the idea is that a disk would be unstable when Q is smaller than 1. And this is, you can see, this is associated with the surface density, the gravity. So basically it means that gravity wins. And here we have the stabilizing parameters. So these are the sound speed, so like the temperature and the angular velocity that actually pushes to the other side. But if this is high enough, then it means the fragmentation can occur. And then the question is, after fragmentation, what about the cooling? Can these objects really cool down and remain gravitationally bound? So this is something that is still being investigated. The efficiency of this mechanism is still being studied. We need to see whether in realistic disks fragmentation can occur. The masses of the forming clumps is still being debated. Some people say it can lead only to the formation of very massive objects like brown dwarfs. On the other hand, some simulations suggest that you can form also much smaller objects. So the pros of this formation mechanism is that it leads to fast formation because it's a dynamical process. It's efficient at large radial distances, so this can explain some of the giant planets that are observed at very large radial distances, like HR 8799. But it also has cons, so one needs rather massive and cold disks, and the survival of the clumps as well as their final masses are still not known. In the last few years, there's been a lot of progress in understanding what are the properties that are predicted in the disk instability model. And here I just show a few examples. These are results from population synthesis models. But as I said, this is still work in progress. This is because not only that simulating this formation mechanism typically requires a lot of computational resources, there are physical mechanisms that have to be entered, and this is hard to model. So we are still in the process of giving good predictions for the disk instability model in terms of the masses of the clumps or the planets and when they are, where they are located. And here you can see from Fogan et al. 2018, this is the mass of the clumps versus radial distance. So here you see the object mass and the radial distance in astronomical units for different core masses. And basically you can see the population. Here you have an example from a paper by Muller et al. Also, you have the mass of the planets as a function of orbital radius. And again, you can see that there are different populations. There are massive objects, less massive objects. Some are located at short radial distances, some at larger ones. But again, as I said, this is still being investigated, and there are many assumptions, simplifying assumptions, and we are trying to add more and more physics to come up with more robust predictions for the populations of those planets and try to use giant exoplanets to test these models and the predictions. But as I said, in the disk instability model, it was often predicted that the clumps that are forming are rather massive, so in the brown dwarf regime. But actually, in a recent study, we showed that if one accounts for the magnetic fields, clumps can be much smaller in terms of mass. Actually, clumps with the mass of Neptune and lower can be formed. And this is because the magnetic field is basically shielding these small protoplanets, and that limits their gas accretion and their further growth to larger objects. So it can actually be that the disk instability model can lead to the formation of smaller objects. So as I said, this is something that is still being investigated. But in this talk, I will focus on the standard model, which is the core accretion model. And the nice thing about this model is that it can explain basically not just the planets in the solar system, but the different planetary types that we observe around other stars. And here I show you a schematic plot of this formation mechanism. So what you see here is the planetary mass. This is typically given in Earth masses as a function of time. This is typically in million years. And the exact numbers, they really depend on the model assumption. But the idea is that in this formation model, we have three main phases. So we have the first phase, and this is the formation of a heavy element core. And as I said, this can be via planetesimal or Pebble accretion. And if you stop forming the planet at that stage, you end up with a terrestrial planet. Then there is a second phase when it comes to giant planets, when you have accretion of hydrogen and helium. This occurs when the core is massive enough to start to accrete gas from the disk, assuming that the core formed fast enough so the gaseous disk is still there. And here we can see this is something we call phase 2. So you have an object that looks a bit like that. Okay, so you have a steady accretion of hydrogen helium gas. The heavy element accretion is moderate, and this is, you can see the total planetary mass. And if you stop the formation of the planet at that stage, you end up with something that is like Neptune or mini Neptune. So basically you have a planet that is dominated by heavy elements, but also have some hydrogen helium envelope. And then if the planet forms fast enough, it can reach the third phase, phase 3, which is runaway gas accretion. And this is when the gas accretion rate exceeds the heavy element accretion rate, and we have runaway growth, and we have the formation of a gaseous planet, and you can see it here. And if you go through this state, you end up with a gas giant planet. And what stops the accretion of the gas, we think that it's either the formation of a gap in the disk, or it could be basically the disappearance of the disk if it happens. If it takes a few million years to form this planet, then the disk will not be there anymore. So that's basically the process of the core accretion model. And again, you can see that depending on the time scale and depending on the local conditions, you can really explain this diversity. Again, you can form terrestrial planets or only heavy elements. You can form gas giant planets that are mostly hydrogen, helium, and you can form these intermediate type planets. And here I show you an example. This is from Pollack et al. 96, and this was really a breakthrough study when it comes to giant planet formation. Here they show the formation of Jupiter. Sigma here corresponds to the solid surface density, so how many solids there are at Jupiter's formation location. And again, you can see these three phases. So we have phase 1, phase 2, and phase 3. Phase 1 is really dominated by the growth of a heavy element core. So you can see this is mz, that's the heavy element mass. Then we have the mass of hydrogen helium with mxy. So this is the hydrogen helium mass. Then you have the total mass. And again, you can see phase 2, you have a steady accretion of hydrogen and helium until basically they cross, and then we start phase 3 with runaway gas accretion. And you can also see here that actually the phase that takes the longest in this kind of formation scenario is really phase 2. So it's really the accretion of hydrogen and helium. And the reason it takes a longer time is because the planet has to cool down and basically radiate the energy in order to shrink, and then basically accrete more gas because it's still embedded in the disk. So basically the accretion rate of the gas is controlled by the cooling of the protoplanet. And in this study, which is already relatively old, you can see that the formation timescale to form Jupiter was about 8 million years. And of course, now we know that this is probably too long because the average disk lifetime is about 3 million years. So this is probably not the right scenario to form Jupiter, but actually one can vary the formation timescale depending on the model assumption. So if one assumes, for example, higher solid surface density or different opacity, then of course one can really shrink a lot the formation timescale for Jupiter or giant planets in general. Okay, but that was really important because this really shows the basic physics behind the core accretion model. And as I said, now we think that maybe the growth of the core is not necessarily dominated by the accretion of planetesimals, but it might be dominated by the accretion of pebbles. So these are much smaller objects. So we know that in the core accretion, in order to form a giant planet, we first need to form a heavy element core. And the question, is this core a result of pebble accretion or planetesimal accretion? Since pebbles are much smaller and they are basically drifting from the outer part of the disk, they can be slowed down by friction, gas friction, and then they can easily be captured by the protoplanet, unlike planetesimals, which are larger. And you can see that in the sketch from Lambres and Johansen. Here is a protoplanet, and you have an object that enters the region of the growing protoplanet, and you can see that basically the pebble can be accreted very efficiently, while the planetesimal not necessarily, and can continue flying next to the planet. And again, this is just because of the size and because of the role of friction. So if you have smaller objects like pebbles, basically it means that the accretion rate is higher. So you accrete heavy elements in a higher rate, and as a result, you have a faster formation. And that's basically the advantage of the pebble accretion. When it comes to planetesimals, it's different. You have a different accretion rate, and the core stops growing basically when we reach the planetesimal isolation mass. And this is basically when all the planetesimals in the feeding zone of the planets have been captured. This is different from the pebble isolation mass, which is basically when the core grows high enough or massive enough to generate a pressure bump that basically would trap all the drifting planetesimals, the drifting pebbles outside its orbit, and then you don't accrete pebbles anymore, and this is known as the pebble isolation mass. So the pebble isolation mass is associated with a pressure bump in the disk, while the planetesimal isolation mass is associated with basically depleting the feeding zone. And as I said, we'll have a look at some of these papers. There is a lot of activity in this direction, and each of this scenario, pebble accretion versus planetesimal accretion, also has different, somewhat different outcomes, not just in terms of the formation timescale, but also what are the properties of the forming giant planets. And again, this is something that we are still investigating and really developed a lot in the last few years. An interesting thing I would like to mention is that recently, in 2017, there was a paper by Coir et al. Where they actually looked at the solar system, and they used meteoritic constraints to say something about the formation timescale of Jupiter. And in this paper, they show that there is evidence for two reservoirs of meteorites that have been separated between 1 and 3 million years after CAI formation, where when Jupiter basically had an intermediate mass between 20 Earth masses and 50 Earth masses for these 2 million years. And of course, that's important, because if this is true, it puts some constraints on the formation path of Jupiter. And you can see it here in this sketch. So here you have the time after CAI formation, and basically the idea is that initially you have drift of objects, of solids, and then Jupiter reaches pebble isolation mass, right? And then you cannot accrete the pebbles anymore, and you have 2 million years between Jupiter reached pebble isolation mass of about 20 Earth masses and a mass of 50 Earth masses, and that had to last 2 million years. And then at some point, once Jupiter was 50 Earth masses, it was large enough again to scatter the objects and then mix these two reservoirs again. So the point that is important here is that they predict that Jupiter had to stay in the mass of 20 Earth masses and 50 Earth masses within 2 million years. And for people who work on planet formation, this is pretty surprising, because once the protoplanet starts to accrete gas, that happens really fast, because this is when we have phase 3 and we have accretion of gas in a runaway fashion. So this is what we have in phase 3, so runaway gas accretion. And the question is, how can it be that a growing giant planet remain at this mass of a few tens of Earth masses for such a long time, of like 2 million years, without accreting substantial amount of gas and running to become a gas giant planet? And we looked at that And this paper was published also a few years ago, basically trying to explain this scenario when you have this gap of 2 million years in Jupiter's growth, remaining just with a mass of a few tenths of Earth's masses. And the solution is that probably both pebbles and planetesimals are important for the formation of giant planets. And this was published in Nature Astronomy. And basically, this is the idea, is that first, Jupiter's core was growing by the accretion of pebbles, and later there was a stage of planetesimal accretion that led to the delay of runaway gas accretion. And you can see it in this sketch. So here I show these three stages. So in the first stage, you have the growth of Jupiter's core by pebble accretion. The protoplanet could excite large planetesimals that lead to fragmentation, so to the formation of smaller planetesimals. Then Jupiter is massive enough to prevent pebble accretion, so basically pebble isolation mass is reached. And then planetesimals are accreted, but the energy that is associated with the accretion of small planetesimals prevents rapid gas accretion for 2 million years. And this is because whenever planetesimals are accreted, they provide energy, and then again, the planet has to cool down before it can accrete more hydrogen and helium. So if you have efficient accretion of solids in the form of planetesimals, basically it can delay the setup of or the onset of runaway gas accretion. And then at some point, Jupiter manages to go to the runaway gas accretion phase at about 3 million years, and a giant planet is formed, or Jupiter has been formed. So have a look at this paper. Again, it's an interesting idea to try to explain this constraints from the solar system when it comes to the meteorite records. But now I want to move on, and I would like to make a connection to planetary interiors. So when it comes to the formation of giant planets, of course, we want to understand the giant planets in the solar system, but we also want to understand exoplanets, so giant planets around other stars. And we really want to have the connection to the planetary interior in the sense that we want to know what is the predicted composition of giant planets for different scenarios, formation scenarios or formation conditions. What is the core mass? How many heavy elements are there? How they are distributed in the planet, and so on. So luckily in the solar system, when it comes to Jupiter, we have the Juno mission, the NASA Juno mission, that provided very accurate measurements of Jupiter's gravity field. And that allows to have, to make very accurate models of its deep interior. So basically we make structure models of Jupiter. Of course, this is non-unique, so you cannot really say what is the exact composition and structure of Jupiter, but one can use different equation of states, different model assumptions, and see what structures can fit the gravity data as measured by the Juno spacecraft. And it was found already in 2017 that the only way to fit Juno data is if you have inhomogeneous interior in terms of composition in Jupiter. And that means that the heavy element mass fraction, or in the deep interior of Jupiter, is not the same as in the outer envelope. Okay, so it means it's not fully mixed, it's not homogeneous. This is very different from what people thought for years. The giant planets are just spheres or balls that are fully mixed and have the same composition everywhere. This is definitely not the case when it comes to Jupiter. And in addition, there is an indication that Jupiter does not have a compact pure heavy element core, but it has something which we call a fuzzy core or a dilute core. And this is basically when you have a composition gradient in the deep interior, and you don't have a sharp transition between the core and the inner envelope. And you can see it here. So this is the standard structure of Jupiter when you have a compact heavy element core, and then you have the metallic hydrogen envelope and the molecular one. But again, even in this picture, this would be valid only if here you have more heavy elements than here. And again, the more realistic view of Jupiter's interior is this fuzzy core, where you have a higher concentration of heavy elements in the deep interior of Jupiter, and there is somehow a smooth transition to the envelope. And this is important because it can tell us something about the formation history of Jupiter. And as I said, indeed, structure models, the ones from Valletan in 2017, and then also by Devraz and Chabrier, 2019, it was very clearly shown that in order to fit Juno gravity data, you need to have this fuzzy core. So you can have maybe a small, compact, pure heavy element core, but you have a region which is quite extended, can reach up to 70% of Jupiter's current radius, where you have composition gradients and when you have this fuzzy core. Okay, so that's very important to keep in mind. And now we have to ask ourselves, well, how can we link giant planet structure and origin, right? Because this is what we want. Well, that's why we do all these measurements. We see how Jupiter is like today, but in fact, we still want to understand how Jupiter formed. And in order to make this connection, we really need to determine the primordial internal structure of Jupiter, but also model its evolution. Because when we look at Jupiter today, it's not necessarily the same as just after it formed. So this is why modeling the planetary evolution is a critical piece when it comes to linking formation and internal structure. So first of all, we should ask ourselves, where do the heavies go? So these heavy elements that are accreted, the planetesimals or the pebbles, do they really reach the center of the planet, or do they have a different distribution? And this has been investigated by various groups. And here I show you an example from Valletta and Heled, 2019, where we basically took different type of solids, so different sizes and different compositions, and we wanted to see where they are deposited when they are accreted by the protoplanet. And what you can see here you can see the fraction of the heavy elements in the envelope as a function of normalized radius, and the different colors correspond to different times, and this is in million years. So you can see that at early times, when the planet is just growing, most of the heavy elements that are relatively large, they are really deposited close to the core, not in the core, not in the center of the planet, but relatively close to the center. But then as time progresses and the planet can accrete hydrogen and helium gas, you can see that the heavy elements are actually deposited further and further from the center of the planet. And that tells us that actually we should not expect that most of the heavy elements in giant planets are in the center of the planet, but actually that they should be distributed along the planetary interior. And we find that no matter what type of solids we assume and what the composition, so size and composition, the core itself always remains pretty small. And when I say pretty small, it means a couple of Earth masses, not more than that. So, you know, this old way of thinking that Jupiter has a very massive core of 15 Earth masses or 10 Earth masses, we don't see that in the models. And here we can see just a comparison between solids that are 10 meters versus 100 kilometers. So if the solids are large, like 100 kilometers, planetesimals, they tend to be deposited closer to the center, and when they are smaller, further out. But again, they don't reach the core, even when they are very large planetesimals, like 100 kilometers. And that brings me to the next question, which is actually, how should we define the cores of giant planets? Because I just told you that, you know, it's not a strict boundary. And historically, in this Pollack et al. Model, it was assumed, not found, assumed that the total heavy element mass is the same as the mass of the core. But that was just done to simplify the calculation. And as I said, various studies show that once the core reaches a few Earth masses, most of the accreted heavy elements really remain in the envelope. So we do not have this core plus envelope structure, even when we build up the giant planet. So how should we define this the core of giant planets. And here I have some questions. Is it by the physical state of the material? So, if it's solid versus liquid, is the density, is it the requirement for density discontinuity? So if I have some kind of a density jump, is that the region of the core? Is it the stability against convection? So if I have something which is stable, so radiative or conductive, and then something convective, is that where I should define the core, a little bit like one does in stars? Or is it a fraction of the high Z material that is high enough? And I think, to me, this is a reasonable definition. But again, this is just to make the point that actually we don't have a very good definition for cores of giant planets. And that means that next time when you read a paper and you have an estimate for the cores, for the mass of the core, you have to ask yourself, hey, how did they actually define the core mass? Because different people define it in a different way. And again, there is no one true answer because it's so complex. And indeed, from formation models, we see that there is this buildup of composition gradients in the deep interior due to the accretion of planetesimals and pebbles as the planet is growing. And you can see an example here. So here you have the heavy element mass fraction as a function of normalized mass. This is when the planet reached a Jupiter mass. And you can see that really you have a gradient, and there is no way to define where the core really stops, because you can see that it has a composition gradient. And for that, we can definitely conclude that cores of giant planets are fuzzy. Again, the core is not distinct from the envelope. The core region, or the innermost region of the planet, is not pure heavy elements. It also includes some hydrogen and helium. And if you have a composition gradient, which is steep enough in the deep interior of giant planets, it also means that they are not fully convective and not adiabatic. And that's also important when it comes to the characterization of giant planets, because this is an assumption that is often made, that assuming that giant planets are fully mixed and fully adiabatic, and this is probably not the case. And then also in 2017, basically, we made the point that really cores of giant planets are fuzzy, so there is no strict definition for giant planet cores, but we also showed that the heavy element distribution in the planet could be related to the accretion rates, or more particular to the ratio of the heavy element accretion and the gas accretion. And here I show Z as a function of Z of M as a function of time. These are just for two formation models aiming at Jupiter, just assuming different solid surface densities. And you can see that the distribution is rather different. And this is just by changing the available solid material that can be accreted. So that, of course, affects the accretion rates of both the heavies and the hydrogen helium. And that means that just by changing a little bit the formation conditions, you end up with a planet that has a different internal structure. So that makes everything more complex, but it's also pretty cool. And of course, that's also important because if giant planets, young giant planets, have this kind of more complex internal structure, it has important implications for the evolution of the giant planets and also for their characterization. So again, if no significant mixing occur, we suggest that the heavy element distribution reflects the ratio between the heavy element and gas accretion rate, and we came up with this equation. And that tells us that if we manage to constrain the heavy element distribution in giant planets, assuming that no substantial mixing occurred, we can tell something about the accretion history. And again, the interesting thing is that just by slightly changing the conditions, like I showed you before, and this is now shows the heavy element mass fraction as a function of normalized mass up to Jupiter, you can see that the distribution is pretty different. This is much more core plus envelope structure, and here the composition gradient is much more gradual. And this is interesting because it tells us something about the diversity of exoplanets. And in a recent study led by Claudio Valletta, we basically checked this approximation. So you see the orange really corresponds to this equation we came up, and the black is the calculated heavy element profile using numerical calculations. And we see that when it comes to planetesimal equation, well, the approximation is pretty good, although you have these jumps, and this is because of fragmentation of the planetesimal. So it leads to local peaks sometimes. And this is the same thing, but when we allow Jupiter to grow by Pebble equation, and again, you can see that the calculation is in very good agreement with our approximation. And the conclusion from that is that the heavy element profile within the deep interior of giant planets, and this corresponds to before runaway gas equation. So this is when we still have substantial equation of heavy elements. So this profile reflects the equation history of the planet. So this is really a big step forward. What about the stage of runaway gas accretion? So what is the efficiency of gas accretion? This is also something that is still being investigated. This is often calculated with 3D models that look at the accretion, because it's not a 1D process, and there are different formulas for that. And I don't know what is the right one. And of course, as I said, this is also something that is being investigated. But the point is that based on what you're using or what you assume in your model, you would get a different formation timescale. And here you can see 3 different prescriptions for the gas accretion during runaway. And you can see that also when you assume different alpha viscosities for the disk, you really have different timescales to form the planet, and that also leads to different luminosities for the planet. And that's important when it comes to direct imaging, because as you know, we take the luminosity of young planets and then we try to use that to infer the mass, but actually it's not just the mass that determines the luminosity, it's actually also the accretion rate itself. So that also means that we really need to better understand the efficiency of gas accretion when giant planets reach this runaway gas accretion, because it really would not only change the formation timescale, but the luminosity of the young planets. So when it comes to Jupiter, as I said, we think that what happens is that first Jupiter core grew mostly by accretion of pebbles, followed by accretion of planetesimals and gas, and at some point it was really mostly accreting hydrogen and helium. And here we can see the heavy element mass fraction as a function of mass ending at Jupiter mass, and here you can see an example of a formation scenario. So here we can see that's the mass in Earth mass as a function of time, and this is the heavy element mass versus the hydrogen helium mass, and you can see that actually runaway gas accretion occurs a bit later and at higher masses. But as I said, this is something that is still being investigated. The fact that we know that composition gradients are likely to form during the growth of giant planets is also important, as I said, for the evolution of the planets. And this is because the fact that you have composition gradients in the deep interior, it means that these composition gradients can inhibit convection, and that means that the cooling of the planet is different. But in fact, it's not just the distribution of the heavy elements in the deep interior that can inhibit convection. It's also the value of the entropy or the entropy contrast that you have between the protoplanet and the accreted gas. And you can have a look at these papers, and there we show that actually you can have quite a contrast in terms of the entropy when you reach runaway gas accretion. This is linked to the accretion shock, so it can be very hot, so very different entropies between the accreting protoplanet and the gas. And this by itself, the fact that you have these different entropies, can lead to the development of radiative envelopes. And so it means that, again, the planet is not convective. And that means that if the planet is not convective, it's less likely to be fully mixed. And of course, if you have this effect of the entropy contrast and you have composition gradients, it tells us that it's much harder to use, for example, the luminosity to determine the mass of the planet or to constrain its formation mechanism. And here you can see the luminosity as a function of time. And this is just when we looked at one Jupiter mass found in a co-accretion model, and this was without composition gradients. And you can see that based on different model assumptions, especially at early times, we get very different luminosities. So that's also just to tell you that this is important to model the late stages of gas accretion in a proper way. So the treatment of the shock can really influence how the outer convective zone grow inwards and how long it takes basically for the planet to be fully mixed. So here are different accretion rates and different treatments of the shock. Yeah, so you can have a look at this papers to get more information. And in this particular paper, we showed that although initially we start with this is the entropy as a function of normalized mass, we start with something that has a entropy gradient, which means that the planet is not fully convective. As time progresses, basically the planet cools down and the entropy becomes constant, which means that the planet becomes fully mixed. But this is not accounting for the distribution of heavy elements or composition gradients in the deep interior. So this we've done a bit later. But even if you ignore that effect for a second, just by the fact that initially the planet is not fully convective and fully mixed tells you something about the characterization of giant planets, that it's not that straightforward because the cooling of the planet will be different. And again, if you also account for the fact that you have composition gradients or you want to mix some of the material, if it's not fully convective right away, it means that you have to wait a while before material can be mixed in giant planets. So again, this is very important when it comes to giant planet evolution, which is my next topic. So really, how do giant planets evolve after their formation? Typically, once they reach their final masses and then the gas disk has dissipated, basically what happens is that the planet contracts and cools down on timescale of gigayears. So this is typically not much is happening because things occur on a timescale of gigayears. When it comes here, you can see the radius as a function of time. So really most of the evolution, most of the changes occur at early time. So here you can see the contraction of the radius. So you can see how the radius shrinks. This is the effective temperature and the luminosity. But again, it is important. The things are changing, although relatively slowly. This is a completely different time scale in comparison to the formation of the planet. But the important thing is that as the planet evolves, actually the internal structure can change if you have, for example, composition gradients and convective mixing, because you can shift the location of material. You don't change the bulk composition, but you can change the internal structure. And in this particular study, we assumed a heavy element distribution that you can see here. So this is Z as a function of normalized mass for Jupiter. And we just wanted to see what happens in terms of mixing. And we found that at early times, convection is rather efficient, and then it can erode this composition gradient. So you can see the dashed blue one is the primordial one. And here you can see what happens as time progresses. So you can see that convective mixing can erode the outer part of the composition gradient, and then here everything is mixed and adiabatic, but not the deep interior. So what we find is that most of the mixing occurs at the first 10 million years of the evolution, and this is because this is really when the planet contracts and is the hottest and convective mixing is most efficient. But we also show that the outer part of Jupiter is expected to be fully mixed, while the deep interior could remain stable against convection and have this composition gradient. And this is really great because this is somewhat providing the link between these formation models that I told you that predict the existence of composition gradients and structure models of Jupiter that also suggest that Jupiter has this fuzzy core. And we show that in terms of the evolution, really one can sustain these composition gradients. But I have to say that this composition gradient that was assumed, the primordial one, was not based on a particular formation model. And what we've done later in 2020, we looked at different formation scenarios and wanted to see whether we can have a planet with a primordial composition gradient like that. So we took different equation weights and different treatments of the gas equation. We had hot and cold starts, and we wanted to see how things change. And what we find is that not in all cases this composition gradient can persist. If the planet is hot, and this is what we find that happens most of the time, actually convection is very efficient, and this composition gradient is likely to be mixed. So while we do show that composition gradients are likely to occur, we have a hard time to make them very extended, these fuzzy cores, to go to 70 or 60% of the planetary radius. So more detailed formation models are needed in order to expand that, in particular, the fuzzy core of Jupiter. Okay, so here we come to my summary and conclusions. The mechanism for giant planet formation is still being investigated. Core accretion is the standard model, but the exact conditions are not known yet, and the physical processes matter, and they can really affect the planetary formation, the predicted primordial structure, and the long-term evolution. Giant planets are complex. They are not just spheres of mixed material, fully adiabatic. They have complex internal structures. They are inhomogeneous, not fully convective, and are likely to have fuzzy or dilute cores. The composition and internal structure of giant planets are linked, and basically we cannot connect composition and internal structure with formation without understanding the formation history and evolution history of giant planets. Thank you very much, and I look forward to meeting you in the live session.